Oh, hey, didn't see you there. My name is Tyler Sensala, and today I'll be talking about metal nanoparticle deposition. Specifically, I will be presenting on e-beam evaporation. Here's a schematic of an e-beam evaporator. The e-beam evaporator operates under a vacuum. This allows electrons produced from the tungsten filament to bombard the target material. The target material will turn into a gaseous phase when bombarded by these electrons and precipitate onto the substrate as a solid continuous film. To obtain good adherence of the target material, the substrate should be clean. This is the e-beam evaporator located here at Louisiana Tech University in the IFM. The advantages of e-beam evaporation over the other methods such as thermal evaporation are deposition rate, efficient use of target material, and better film morphology. I will now walk you through this process. First, I will introduce some of the materials that will be needed for this process. A e-beam evaporator, the targeting material, as well as a substrate. This is an SEM image of the substrate before deposition. Notice the grain structure of the film, as SEM images will be periodically shown throughout the process. Now we'll move on to taking a look to the inside of the e-beam evaporator before operation. In the e-beam evaporator, we have a crucible that holds the target material. We have a filament that heats up when a voltage is applied, and electrons are drawn from this filament to heat the target material. Now we'll move on to the under operation, which you'll see the material rising up to the substrate above. The first step is to turn on the voltage supply. With the voltage supply on, the target material will be heated and precipitated up to the substrate. The target material is now heated to where it needs to be and is starting to precipitate up into the substrate. Here's the thin silver film deposited onto the substrate. As you can see, it is a continuous film. For this reason, to get the metal nanoparticles that we desire, we must first anneal it. Here is an SEM image of the substrate after deposition. Notice that you can no longer see the grains of the substrate because of the thin continuous metal film. For annealing, we will set a thermal source to 200 degrees Celsius. During the annealing process, the thin metal film coalesces into distinct metal nanoparticles. After annealing at 200 degrees Celsius for 1 hour, you can see there is a distinct array of metal nanoparticles. Here is an SEM image of the substrate after annealing. Notice that an array of nanoparticles has been obtained. Additionally, notice that the nanoparticles are not all the same size. After fabrication of a metal nanoparticle film, it is important to analyze its optical characteristics. To analyze this film, a Filmetrics 10RT thin film analyzer will be used. This analyzer works by first placing the sample face down right here, where light is illuminated up through the bottom and up into this detector. The amount of light that reaches this detector determines the transmittance and reflectance data available on the computer screen. Before measurement, the sample must first be acquired. Then, a standard, an aluminum oxide reference, must be used. Then the the stage is measured without anything on it to collect the background light. And then a background filter is used to determine the amount of background light currently present. After measurement, a transmittance and reflectance curve will be obtained. Here you can see the transmittance curve, and here is the reflectance curve. Here is a summary of the transmittance data through the metal nanoparticle deposition process. The blue line represents the substrate before deposition, the gray line is the transmittance after deposition, and the yellow line is after annealing. As you can see, metal nanoparticles improve the transmittance data of this substrate. Well, that concludes my video on metal nanoparticle deposition. I hope you learned a little bit about e-beam evaporation, as well as how metal nanoparticles can improve optical data.